So last time we finished sort of one segment of what we were trying to do, which is we were looking at completions of both discrete and continuous time systems. And so in the discrete time case, what we found was the completion of little c finite, meaning finite support. And in the continuous time case, we found the completion analogously. Well, analogously in concept, but not in detail, of continuous compactly supported signals on continuous time domain. Okay. So that's good, and this gave us large classes of discrete time signal spaces here and continuous time signal spaces here. Okay, and the completions here we were able to describe relatively easily by making reference to sequence spaces. Here, the completions, particularly in the p less than infinity case, were more difficult to come up with, but we have those things now. And again, that gives us a large class of signals to talk about. And so, for example, we will talk about all of these kinds of things, both discrete and continuous time, when we talk about Fourier transforms, okay? But before I do that, I want to kind of finish talking about spaces of signals, because there are interesting classes of signals, and we've encountered some of them, just as examples of things that don't fall into these classes that are not in the completion of this or in the completion of that. Okay. So what we want to do is we want to extend spaces of signals to allow for example, very benign type things, to allow for f of t equals, say, t, maybe defined on the entire real line, okay, or similarly, f of n delta in the discrete time case is equal to n. Okay, so there's nothing particularly obscene about things like this, but they don't fall into the class of signals, and so here we're going to take for this signal we're going to take t to be z delta, and for this case we're going to take t to be r. Neither of these guys are in the completion in the discrete time case of this or in the continuous time case of that, but they're still interesting things, and we'd like to be able to talk about them. Okay, and the problem is that these are unbounded in some way. Okay. Okay, well, in some way which prevents their inclusion in these spaces. Okay, good. So how are we going to do that? So let's first look at the discrete time case, where things are very easy, but almost confusingly easy. Okay, so we're going to let t be a discrete time domain. All right, and as always, F is our set of scalars. Okay, now, how are we going to come up with a definition of a space of signals that includes signals like this? Okay, and well, you know, there is obviously a space of such signals. You could just consider the space of all signals. Okay, so then Ft is simply the set of all mappings from T into F. Okay, so there's our space. Now the problem is, how do you, you know, put some useful analytical structure on here? You know, we had talked about norms here. Okay, well, and none of these norms are applicable, but we do something which is quite similar. Okay, so for each finite sub time domain S. Okay, so you know, S. The point is that S itself is a time domain. So it's a finite set of points, but it's, you know, a finite set of points which are adjacent to one another in T. Okay, so we have a finite collection of times S. We define a, sorry, and I'm going to, and for P in here, okay, I'm going to define a seminorm. Remember that a seminorm has the properties of a norm, except the definiteness property, right? So it's possible that for a seminorm, you can have a non-zero signal with zero seminorm, okay? And it's going to be defined like this. Okay, so now I'm going to include in the notation here the fact that this seminorm is going to depend on S. Okay, and here's the definition. And so it breaks into the two cases. I'm going to do them both at once. In the P equals infinity case, we get the usual thing that we expect, the sup norm. But now over S, okay? This is valid for P equals infinity. And then in the, in the P less than infinity case, we get the usual sum. But again, you only do this over S. Okay, now because S is finite, these always are well defined, meaning they're less than infinity. Okay, and these are easily verified to be seminorms. Okay, but they're not norms. All right. Okay. So how do you make use of things like this? Okay, so we're going to make use of things like this by virtue of describing what. Okay, so we wish we use the family of seminorms So you don't just have one norm, you have a family of seminorms. And S, and you run this family is labeled by finite sub-time domains S of T. Okay, to give a topological structure. To FT, okay? And the way we do this is I will define this topological structure by telling you what convergence what convergence sequences are. Okay, so to describe this structure, okay, we describe the convergent sequences in FT. Okay, and so the definition is going to be that a sequence Fj in Ft converges to F if the sequence F restricted to S, Fj restricted to S, converges to F restricted to S. Okay, so now I'm going to choose an S, and then I'm going to restrict all of my signals to S. Now on S, so S is allowed to vary here, but once you fix an S, for the set of signals in here, restricted to S, this is a norm. Okay, so it converges to Fs in the norm. Okay, and so I'm for the time being, and we'll quickly see that it doesn't actually matter what P you use, but I'm going to fix a P in here. Okay. All right. Okay, so that's how you describe convergence here. All right, so let's maybe take a look at an example so we can see what convergence looks like. Okay. All right, so let's look at our example here. All right. Let's take, and so I'm only going to do that example. Let's let T be Z delta. So signals, the time domain goes from minus infinity to plus infinity. And let F of N delta equal N. Okay. So this is a signal that at delta 2 delta minus delta, minus 2 delta. Okay, so it takes a value 0, oops, 0 here, 1 here, 2 here, and so on. Okay, and then minus 1 here, minus 2 here, and so on. Okay. Okay. So let's let f okay, so now according to the rule, we're going to take a finite subtime domain S. Okay. And we're going to think about convergence of this sequence to this signal. Okay. All right. So then, okay, let's let the approximating sequence fj. Oops. Okay, so this is going to be the sequence, which is fj of n delta is going to be n, when n is less than in magnitude, less than or equal to j, okay, and 0 otherwise. Okay, and so this is going to be, so F1 is just going to be this bit, okay, and then 0 otherwise. F2 is going to be all of these parts, and then 0 otherwise, okay? And so we're chopping this function off, where fj takes f and chops it off between minus j and j, okay? All right, so we claim then that fj converges to f. Okay, so I'm going to move this business down here since I put it in the wrong place. Like so. Okay. All right. So to prove that this sequence converges to that one, I need to show that if I restrict it to any finite subtime domain S, then I get convergence of the restrictions to S. Okay, good. So how do we do this? Well, what you can do is you're going to choose J large enough so that S is contained in the set of times from minus J delta to plus J delta. Okay. So, so I'm going to let N be such that S is contained in minus n delta. Okay, so I can always do that for large enough n. So then for j greater than or equal to n, I simply have that fj restricted to S is equal to F restricted to S. Okay, and so thus clearly Fj restricted to S converges to F, restricted to S, okay? All right, so so that's how this mode of convergence works. It's a very flexible kind of convergence, all right? And so it means that if you kind of restrict to any bounded collection of times, that on that bounded collection of times, in the discrete time case, that means finite, you converge in the norm, okay? Now, there's a facet of this that comes out through this example, and that is that this convergence doesn't depend on P. So this is only in the discrete time case. So in the discrete time case, a convergence doesn't depend on P. Okay, so if it converges for one P, it converges for all P. And so this means that you can really use any of these P norms in the case of discrete time signals. And the reason for that is very simple. That if you choose a finite subtime domain T, and you're to talk about convergence, you're restricting to that finite subtime domain. This is really convergence in a finite dimensional vector space, okay, namely the vector space of signals on S. Okay, and we know that for finite dimensional normed vector spaces, convergence and all concepts associated with topology, continuity, etc., do not depend on the norm that you choose. Okay, and so for this space, you can use whichever of these norms you wish to talk about convergence. Okay, that's not going to be true in the continuous time case. Okay. All right, so in the discrete time case, this process gives you a way of topologizing the set of all discrete time signals on your time domain. Okay, and in the continuous time case, of course, that's not going to be so simple. Okay, all right, so let's take a look at how this works in the continuous time case. Okay, so here we're going to let T be a continuous time domain, meaning an interval. And as always, F is in our set of scalars. Okay, so now, what are the kinds of signals that we would like to be able to, talk about convergence sequences for? Here, it was, in the discrete time case, it was all signals. Well, we know we're not going to be able to work with this space in the continuous time case, all right? But we're going to work with adaptations of the things that we're familiar with. And what are those? Those are continuous signals and LP signals, okay? So the two kinds of spaces we work with are the following. Okay, so there's C0. Okay, so this is all continuous signals. Okay, with no restrictions about boundedness or compact support, just all continuous signals. And then we work with the space which we call LP loc. Okay, and this is F with the property that F restricted to S is in LP of S for any compact, not bounded, compact S in T. Okay, so when you restrict your signals to compact subintervals, so S can be compact, but let me, just for simplicity, make this a sub time domain. Okay, which in this case means a subinterval. Okay. All right. Okay, so these are the two spaces we're going to talk about. And so we're going to, put a norm or on each of these spaces in, more or less the obvious way. Okay, and what we're going to do, of course, is we're going to replace the finite subtime domain S with a compact subtime domain, and then kind of do the continuous time analogs of those constructions. All right. So for P in 1 to infinity, okay, define. Okay, so actually I need to do this a little bit more slowly here. So first let's define the infinity case first, since that's what I wrote down first. Okay, so for P equals infinity, we define a family of seminorms like so, and so the notation's the same. We have a subinterval, compact subinterval S, and then this is the P we're talking about. Okay, and the family is again indexed by compact subtime domains S. Okay, by, in the obvious way, F S infinity is sup T T in S. Okay, and now notice that this is well defined because F is continuous still, and so certainly when you restrict F to S, as we're doing inside the soup, that resulting continuous function on the compact interval S will be bounded. Okay, so this is perfectly well defined, and it has the properties of a semi-norm. Okay, and so for P, equals. So for P from 1 to infinity, we define family. And so I neglected to say here, I'm sorry, F here is in C0. Okay. So again, we define a family of seminorms S, P on, and these of course are going to go on LP loc. By, okay, so F S P is integral over S F of T P dt. And so I'm following my policy here of using Riemann integral notation for the Lebesgue integral. Okay. All right, as I talked about last time. Okay. And so we end up with a situation which is rather analogous to what we did in the discrete time case, except the only difference here is we have integrals instead of sums. Okay, so we can define a notion of convergence in exactly the same way as we did before in the discrete time case. Okay, so a sequence all right, so I'm going to let P be in here. Okay, and we take C0 of T when P is equal to infinity and LP log T when P is in 1, 2, infinity. I just want to talk about both cases together. Okay. Okay. So to do this, I'm going to be talking about one of these classes of signals, either this one or this one, depending on what P is. All right. So a sequence Fj in in whatever space. So let me not write it down. Okay. Converges. Okay, so this sequence will be in here when P is equal to infinity, and here when P is between 1 and infinity. Okay, so converges to F in the same space if for every compact subtime domain S okay. The sequence Fj restricted to S converges to F restricted to S, of course. Okay. All right. So we have the same kind of structure that we talked about here. Now, in the continuous time case, there are some things you need to keep in mind that don't arise in the discrete time case. So let's first make sure we understand. So we note that what these spaces LP loc look like. The C0 space, we're kind of okay with that. Okay, let's think a little bit about what that is. So note that LP loc of T F is equal to LP of T F if and only if T is compact. Okay, so for example, so when T is unbounded, then you kind of have no problem with that statement. So for example, this function that we talked about in the beginning, okay, f of t equals t, defined on all of R. Now we have no problem with this thing being an LP loc for any p, because on a compact subinterval S, this thing's continuous, and so it's bounded, and so certainly we'll have a finite p norm. okay, on a compact subinterval. All right, so the unbounded case, we don't find that hard to imagine that these spaces aren't the same in the unbounded case, but let's make sure we understand the bounded case as well. So sorry, the whole point was to consider a special time interval here. And let's consider 0, 1. Okay, so this is I claim that this is going to be strictly bigger than L1 of 0, 1. Okay, so for to show this, I need to find something in here which is not in here. Okay, and let's take f of t to be 1 over t. Okay, now so it's not in here. Okay, because you know, when you integrate 1 over t, you get you know, 2 over t squared or something, or a half over t, 1 over 2t squared or something like that. And that will prohibit you from being in here. Okay. However, you're definitely in here because on any compact subtime domain of the interval 0, 1, this thing is going to be continuous and therefore bounded. And so it'll certainly have a finite p-norm on any compact subinterval of 0, 1. Okay, so beware of that. Okay, so you only get agreement here when the time domain is compact. Okay. All right, and let's look at convergence in these spaces. Okay, so let's let f of t equal 0 on all of R. Okay. All right, so what I'm going to do is I'm going to construct an example of a sequence that converges to 0. Okay, and I'm just going to draw the sequence. So we're going to define fj by, okay, so again, I'm going to draw it. Okay. Okay, so here's -1, 1, 2, 2, 3, 3, and so on. All right. Okay, so F1 is going to look like this. Okay, so it's going to be 0 between -1 and 1. And then it's going to shoot off linearly. It doesn't matter what the slope is. Let's say it's 1. Okay, just for concreteness. Okay, and similarly here. Okay, so it's going to linearly shoot off to 1. All right, and then so this is F1. Now F2 is going to be 0 between -2 and 2, and then it's going to do the same thing as F1. And again, it doesn't matter what the slope is, but let me make it the same as F1. Okay, and then F3 will be the same thing. Okay. All right, so I claim that this sequence converges to F, okay, and remember F is just a 0 signal, okay, in any of these norms. Sorry, I should say it this way, in all of the spaces that I'm talking about. So C0 and LP loc. All right, so here's how you can prove that. So let S T be a compact sub-time interval. All right, let N, rather similarly to what I did in the discrete time example, be such that S is contained in, and let me just be safe here, or just remove any possible ambiguity. Let me go from minus n minus 1 to n plus 1. Okay. Just to remove the kind of boundary points. Okay, so then certainly I have f restricted to fj restricted to s is equal to 0 for j greater than or equal to n. Okay, right, because these functions are 0 from fj is 0 from minus j to j, and so if j is larger than n, then my time domain obviously contains minus n to n. I made it a little bit bigger, and so fj will be 0 restricted to s. Okay, and so thus obviously this converges to f restricted to s. Okay, and this means that the sequence indeed converges to the 0 signal. And so the point is that this is a kind of weak notion of convergence. Okay, it's definitely not anything like uniform convergence. What it is, though, is when p is equal to infinity, it's uniform convergence on every compact subinterval. And when p is not equal to infinity, it's convergence in the p norm for every compact subinterval. Okay, now what's going on outside each compact subinterval for a fixed approximation j can be pretty unpleasant. Okay, so we see here that it's a pretty poor approximation to 0 outside any compact subinterval, but that doesn't keep it from converging to 0 with this notion of convergence. Okay. Okay, so these kinds of signals that sort of don't fit into our normal LP and C0 spaces, they're going to be especially helpful for us to have it on hand when we talk about systems. And the reason is that these kinds of unbounded signals appear in system theory even if we don't want them to. So you can have systems that can take a nice input, say something in L1, let's say, and give you an output which is unbounded in the way that these examples up here were unbounded. Okay. And so you have to be able to consider spaces of functions that are expanded beyond what you have here, because that may not be sufficient to cover what you want. Okay. All right, so that's everything I kind of wanted to say about signals in the normal sense of the word. So maybe it's a good idea to summarize where I'm at. Okay, so in the discrete time case, okay, we have these Banach spaces of signals. Okay, so we have little LP. Okay, we have L infinity. And then we have a little C0. Okay. And we had studied, for example, we had the inclusion relations for these. Okay. All right. So we talked about what the inclusion relations between these spaces are. Okay. So the fact that for example, this one's contained in this one, and all of these are contained in here. And then there was a specific ordering on these depending on P that we talked about. Okay. So we had those, and then we also had the space of all signals f to the t. Okay, and so these ones were normed. Okay, so in fact, there were Banach spaces. And this one is defined by not norms, but seminorms. Okay. All right. Now, in the continuous time case, okay, we had correspondingly these spaces, big LP, there's C0. Okay, so these were normed. Okay, and then we had, C0, 0. Okay, so these were the ones that went to 0 at infinity, and infinity could include an open boundary. Okay, and then the semi-normed ones were LP loc. And C0. Okay, so these ones have semi-norms. Okay, and so there's some loose ends here that I'll polish up. Okay, so there is a space, big L infinity. It's not going to, we won't talk about it too much, but it does come up on occasion. So L infinity, let's define L infinity. So let F from T into F. So T here is a continuous time domain. Okay. Define what we'll call the essential supremum of F. Okay. And so here's what you do. You take the M's in a set of non-negative or non-negative reals, okay, so that the Lebesgue measure of the T's in T, okay, for which the norm of the absolute value of f of t is less than or equal to m. okay? And you want, sorry, is greater than or equal to m, greater than m, is equal to 0. Okay, all right, so let's make sure we understand this part of what we're talking about. So you choose an m, okay, and then you ask, is it true that the set of t's for which f of t exceeds m has measure 0? Okay, all right, so those are, and what we're going to do is over the set of all such m's, we're going to take the infimum. Okay, and so the point is that the essential supremum is going to be the smallest number, okay, for which the set of points where f of t exceeds m has 0 measure. Okay, so it's the essential supremum. So for example, if f of t is equal to 0 for almost every t, then the essential sup of f is equal to 0. Okay, because the absolute value of f will not exceed any positive number on a set of positive measure. Okay. Okay, so then we would define L infinity, well, parentheses infinity of t to be f t to f, so that f, well, first I'm going to ask to f be measurable. And then I'm going to ask that the essential supremum of f be finite. Okay, and then the norm here is going to be the infinity norm. And so there's some confusion here, right? We talked about the infinity norm for this space, but just like here, we talked about the infinity norm for this space and this space. Here, we're going to talk about it for this space and this space. Okay, so the infinity norm is simply just the essential supremum. Okay, so I have these parentheses here that I want to get rid of. Okay, so then L infinity of t is equivalence classes. In L parentheses infinity defined in in the way that we talked about this before. So f is equivalent to g if f of t equals g of t almost everywhere. Okay. All right, so that kind of rounds out one sort of missing part of the picture here. And the other part of the picture that I should clarify is what's the relationship between these various spaces, okay? In the continuous time case. So inclusions between continuous time signal spaces. And here it breaks down by what the time domain looks like. Okay, so first let's look at the case where T is compact. Okay, so in the compact case, the first thing is that C0, okay, of T, well, first thing is, of course, that's equal to C0, as we've seen. Okay, and this is contained in every one of the LP spaces. Okay, and so why is this true? So indeed, right? So that's compact. So indeed. The infinity norm of a continuous F is finite. And so let's just make sure we understand why that implies the P norm is finite. And so F in the P norm, and let me just get rid of the taking the P 1 over Pth root, let me just take the Pth power of the P norm. So this is going to be the integral over T. So remember here, T is compact. Okay, now for each T, that quantity is certainly less than the infinity norm of F. So this is going to be like that. Okay, and this is simply the infinity norm P, sorry, yeah, to the power P of F times the Lebesgue measure of the time domain, which is finite. Okay, so that's what happens in the compact case. And so then you might wonder, what's the relationship between the LP spaces, between themselves? Let's look at that in not the compact case, but the bounded case. So that'll include the compact case. For the LP spaces, that'll include the compact case as a special case. Okay, so let's look at T bounded. Okay, so first thing is that C0 is no longer in LP necessarily. Okay, when it's compacted it is, but not when it's bounded generally. Okay, and we have an example of that we've seen already. And that example was up here somewhere, right? Okay, so here, right? So on this bounded time domain, right, I have this continuous function, and that one is not in any of the LP spaces. Okay. All right. Okay, so, but it's certainly still going to be the case that C0, 0 is going to be contained in LP. Okay, and this is because I'm bounded, so T is bounded, and so going to 0 at the possibly open endpoints of T implies that the function F in here will be bounded, okay, and then the same argument here applies, okay, so that's true. What about the relationship between the LP spaces with the other LP spaces? Okay, so what's true is that P of T F is contained in LQ F. okay, if P is greater than or equal to Q. Okay, and this is for bounded time domains. All right. So let's prove that. Okay, so I need to show that if I take an F in here, then it's in here. Okay, so let F be LP. And define A to be the set of T's in the bounded time domain T, so that F of T is greater than or equal to 1. Okay. All right. Okay, so now I need to show that F is in LQ. All right, so so then I have okay, so then the Q norm of F is equal to, well, the integral over T, and so again I'll raise this to the Q's power just to get rid of the root. Okay, and so now what I'm going to do is I'm going to break this integral up into an integral over A and then an integral over the complement of A. Okay. So it's the integral over A, F T to the Q dt plus the integral over the rest. Like so. Okay. Now, Q is less than P, and on A, F of T is greater than or equal to 1. Okay, and so that means that F of T to the Q will be less than or equal to F of T to the P. Okay, and then here on the complement of A, F is less than or is less than 1, and so this is going to be like so. Okay, and so this is going to be less than or equal to, and then I can make the time domain bigger now. Okay, so that's certainly going to be the case. Integrating positive quantities over larger domains always gets something larger. Okay, and so this is less than or equal to F P to the P plus the Lebesgue measure of T. Okay, and this is finite. Okay, because this is where I'm using the boundedness of the time domain. Okay. All right, so in the bounded case, I get these observations. All right, now, in the unbounded case, okay, then I have that, so I need to think about this one and the LP spaces. Okay, and it's not included in any of the LP spaces in the unbounded case. And the idea intuitively, and this is very intuitive, is that the LP spaces, in order to be an LP, the behavior at infinity for an unbounded time domain should be sufficiently nice that the integrals of the P's powers are finite. Okay, and these guys just go to 0 at infinity, and no matter how you choose P, I can choose something here that goes to 0 slow enough so that its P norm will be infinite. Okay, so that's that. And what about the LP and LQ spaces? Okay, there's no relations at all between those. Okay, so neither is included in either. Okay, so in fact, you can find continuous things in LP and in LQ which violate these inclusion relations. And so what I mean by that, to be precise, is that C0 of T F intersect LP T F. There's no inclusion relations between that and C0 of T F intersect LQ. Sorry, that's an F. Okay. And so the point is to get counterexamples here. You can even consider counterexamples that are continuous. All right. Okay. All right. So I think I've polished up the loose ends that I can think of for the moment. So that sort of concludes the traditional part of the course that has to do with signals. Next time, what we'll do is we'll talk about making our classes of signals even bigger to talk about what are called generalized signals or distributions.